All right, welcome back, everybody. So the last thing that I want to talk to you about this week is a relationship between force and potential energy. And I have copied this relationship over to us. We know, for example, that the change in potential energy is related to the work done by the internal conservative force. And I know how to write work, right? I can write work as the integral of that force times the position, right? The changing position of the objects that are involved. Right? That gives me this really nice expression where if I know what the force is, I can calculate the potential energy. But I might want to go backwards, right? I might know something about the potential energy, and I want to try to figure out the force given that initial potential energy. And so I want to try to figure out, can I reverse or invert this relationship that says the potential energy, the change in potential energy, is the negative integral of f dot dx here. And of course, I can go backwards. Anytime that you are integrating, if you want to go the other way, the thing you want to do is to take a derivative. So that's what I am going to try out here. I'm going to go ahead and guess that the force that I get, that I need in terms of the potential energy is the derivative of that potential energy with respect to x. And I know I've got this negative sign in here, so I'm going to keep this negative sign along here. And I'm going to remember that force is a vector. So I'm going to put a little x hat here to indicate the direction of the force. This particular expression for the force is only valid for one directional forces. So gravity, as an example here, forces, spring forces would be an example. If you start getting into multiple dimensions, then we're going to need to bring some vector calculus in, which we'll be ready for in Physics 213, but we're not quite there. So I want to check to see, is this kind of guess for what the force should be a good one? And I'm going to do that by plugging it in here and seeing what happens, right? So I've got delta U right here. This should be, we're going to find out, equal to the negative integral from xi to xf of the dot product between this thing right here and dx, right? So I've got another negative sign. I need to do du dx, and then I need to do x hat dot dx. Now we've done dot products before. As long as that x hat and the dx are in the same direction, which they are in this example, that dot product is going to give me the magnitude of x hat, which is 1, because it's a unit vector, and the magnitude of the dx vector, which is just dx, times the cosine of 0, which is 1, which means that I can kind of erase this dot product and just replace it with dx, which I could only do because I picked x hat here. Right? If I hadn't picked x hat, if I'd picked y hat or something like that, and said this force is going to point in a different direction, then this trick wouldn't work, and I'd be in multivariable land, and we need more tools for that that we're not quite ready for. So here we go. We've got an integral of a derivative with respect to the thing that we're taking the derivative for. Whenever we have that, we can use the fundamental theorem of calculus to resolve that, right? We also have these two negative signs. We can always smash two negative signs together to make a positive sign. So this would be positive. And then the fundamental theorem of calculus says, take UA at the endpoints, right? UA final minus UA initial, which is exactly our definition of delta UA, right? So this is a big check mark. We got that this worked out. So it turns out that the derivative of the potential energy with respect to x, or whatever variable you are tracking your potential energy in terms of, is related to the force. And I'll send you back over to Canvas, and you can see how this works with an example.